Well, first of all, let me say the procedure that we're doing is something called ANOVA, which stands for Analysis of Variance, which especially for our purposes is a little bit misleading of a name, because this is just another one of the tests for difference between means. Okay? We did one mean versus a specific value, just the t-test. Then we did the difference between two means. Now what we're going to do is the difference between three means. In fact, this procedure, analysis of variance, can be used for the difference between two means, the difference between three means, four means, five means. And you can even cross-classify, which we won't. I might demonstrate at the end of the semester if we have time. But so now we have three groups, and let me. I think I'm going to do this over here. Now, I don't want to. Okay, here we go. So this, just in that box right there, is just one problem. On the other box, we're going to have another similar problem. But there's just the, first of all, let me just ask you, looking at those three groups, does it look to you like there are differences between the three groups, or that they might be the same? It looks different. They're not... each group has its own little spot on the graph. So, when we were doing just two groups, we might have just had X bar 1 and 2. And so we would look at, remember the top would be X bar 1 minus X bar 2, or X bar A minus X bar B. So all we're doing now is adding another group. But when we did the numerator, see if I can do all of this at once here. Remember we had, okay, maybe not. Okay, well, I'm just going all over here with this stuff. Okay, so anyway, we had means of 10, 15, and 20. But, when we did the t-test for independent groups, remember in the numerator we had the difference between the two means. That's the size of the effect that we have. Well, now when we do ANOVA, we're just going to have a third mean in there. We're going to have to find some way of getting differences between not just two means, but among the whole group of three means. So anyway, the other thing that we had in the denominator was basically the variability. What's the height of these white boxes? So when we measure standard error, we're taking... These are really the variation. You can get standard deviation from these numbers, variance or whatever. But the standard error on the bottom was related to how much variability there is in the data. That's what it is. But I want you to look over on the right-hand side. This is another problem. But I want you to notice that it has the same means as we had in the other one. The means are 10, 15, and 20. But it's more difficult to see that there's a difference between groups because the data within each group is so spread out. So, when we've been doing before and what we're doing now, both come down to how big of an effect is there, or how big are the differences compared to how much variability or sampling error there is in the data. So, again, we've got the sample means, that's how big the differences are, and then we have standard deviations, variances, and standard errors, which all talk about how wide the how wide the variation is within each group. borrow your pencil for a second here. I'm just writing down the numbers from each of these problems. We're actually going to go and work these out. Bottom point on treatment 3 over here really should be up a little bit more. It's an 8. Take my word for it. Okay, first thing I want to tell you is this is a big problem. There's a lot of, am I out of it again?
I think it's going to work.
Okay, good. So I'm going to start with the hypotheses. And these hypotheses will stay the same for every problem that we do that's an analysis of variance. The only thing, and I'm probably only going to do 3 groups in here. If there were 4 groups, you would just carry on in the same progression. But HR is that at least one of the following is true. Mu A not equal to mu B. Mu A not equal to mu C. Mu B not equal to mu C, and HO is mu A equal to mu B equal to mu C. So HO is, there's no difference. They're all the same. HR is, there's at least one difference between means. Any one of those 3 being true negates the null hypothesis. Okay? They could all be true, or 2 of them could be true, or 1 of them could be true. If you reject HO, at least one of those. We're going to reject HO if F test is greater than some value. So we're going to have another table now. It's the F table. But it's always reject HO if F test is greater than the value we look up on the table. There's no less than, there's no minus. It's always if it's greater than. And if you'll look on your tables, if you'll turn one more past the T table, you'll see there's an F table for 0.05 level of significance. And we're only going to use alpha 05 in here. You just, well, I could copy you more pages and use other ones, but we're just going to use 05. And you'll notice on that table that in the degrees of freedom, it's got a degrees of freedom numerator, and then it has a degrees of freedom denominator. So the degrees of freedom for the numerator is equal to k minus 1, where k is the number of groups. Remember we had 3 groups, A, B, and C. So that's just 3 minus 1 is equal to 2. Okay. And the degrees of freedom for the denominator is going to equal the total sample size minus k. So total sample size, it's just not the size of one group, it's the whole sample size. So remember I had 5 in group A, 5 in group B, 5 in group C. So that's going to be 15 minus 3 is equal to 12. And so if you look on the F table, you go to 2 and 12, and you should see then that you reject HO if F test is greater than 3.9. By the way, for both of the data sets in those two problems I just showed you, and I'm going to write the number, this part will be the same for both of them. Those are the same hypotheses, and I have the same number of groups and the same sample size, so they're both going to be down to the reject HO if F test is greater than 3.9. The F test is equal to what's called the mean square treatment, which is just going to be the difference between those means, between the 10, 15, and 20. By the way, in this particular set of problems, remember we had means of 10, 15, and 20 in the first one, and 10, 15, and 20 in the second one. The same differences between means. MSTR is going to be the same for both of those problems. Okay? And it's going to be divided by mean square error, which is how spread out the data are. Of course, it's going to be much lower MSE in the first one that we had, and much higher in the second one. You could see by the amount of spreads it was higher in the second one than it was in the other one. So a few things here. Well, I guess I'm just going to go to numbers now. Gosh, I hope I can fit this whole thing on here. I'm just matching these up with the dots that are on that graph. I'm going to do some adding here. First of all, I'm going to get the means for each group. I would write the formula out, but I'm just going to write that it's 50 divided by 5 is equal to 10. Space is at a premium here. So X bar B is going to equal 75 divided by 5 is 15. And X bar C is going to be 100 divided by 5 is equal to 20. Of course, if all the values are 20, the mean is 20. So I'm going to need these values then to get MSTR. Okay. There's one other thing I'll need. I can't see us doing this all on one page now. I could have spread out and give myself some more room in that case. I'm going to go ahead and write down here X bar bar. That's the mean of the means. And it's going to equal, X bar A plus X bar B plus X bar C divided by the number of them, which is K. And that's going to equal 10 plus 15 plus 20 divided by 3 is equal to 15. So I'm still going for my ambition of getting this all on one page. It's going to be tough. MSTR is basically going to be, I'm going to take each of those sample means and get the distance from the mean of all of the means. And I'm going to use that to get the effect of the means. And so it goes like this. MSTR is equal to NA x bar A minus x bar bar squared. So I'm weighting it by sample size, and I'm getting the difference between this sample mean and the grand mean. Now I'm just going to do the same thing. NB x bar B minus x bar bar squared plus NC x bar C minus x bar bar squared. So it's the same thing, just repeated for each one, and that's divided by k minus 1. Okay. I will give you that formula and that formula in any exam or anything. Those will be on the board. I'm going to move over a little bit here. There were 5 in Group A, and the mean of Group A was 10 minus 15 squared plus 5 times 15 minus 15 squared plus 5, 20 minus 15 squared. And that's going to be over 2 for k minus 1. And so that's going to equal, in this first one, 10 minus 5 is minus 5. Squared is 25 times 5 is 125. Plus the next one's going to be 0, because 15 minus 15 is 0. Plus, and the other one, 20 minus 15 is 5. Square that, you get 25. Multiply that by 5, and you get another 125. Divide all.
Work out like that.
Hmm?
Do you find it hard to work out like that?
It's nice when things do work out, I'll say that. Anyway, that's 125. So that's the top. And again, that's going to be the same for both of the two problems that we're working. The differences between means were the same. And that's all this MSTR is doing, is it's getting the difference between the means. Okay. Gosh, I'm trying to think, where can I put this? Gosh, I don't know if I can do it. Okay. MSE is equal to S squared A plus S squared B plus S squared C divided by K. In other words, I'm going to compute the variance of each group and then just take the average of them. That's the mean of the squared errors, or the mean of the variances. So that means that in Group A, the mean was 10. So I've got to get the deviations, and then I have to square the deviations. So the mean was 10. Square those. That's 2. So I would normally put this right down here, okay? I'm going to put it over here. S squared A is equal to the sum of the squared deviations divided by n minus 1. In other words, it's just the same thing as standard deviation, except don't take the square root. This is S squared, not S. So in this case, that's going to equal 2 divided by n minus 1. There are 5 values here. Minus 1 is 4, so that's 0.5. So for B, I'm going to do the same thing. Subtracting 15 from each one. got 4. So S squared B is going to equal to 4 divided by 4 is equal to 1. S squared C is 0. All the values are 20. There is no variation around the mean. I don't need to calculate anything for that. They're all the same. The variability is 0. So now I'm going to come back over here, and my MSE was 0.5, that's S squared A, plus 1 for S squared B, plus 0, divided by 3 is equal to 0.5. That's MSE. That's 250. And 250 is greater than 3.9. So we reject HO. And we conclude at least one of the following is true. We've rejected HO. We've said that they're not equal.
Is there an easier way to do it than having to do every one of those calculations?
But yeah, you can put it in a calculator. There's no better way to understand what ANOVA is than going through these calculations, in my opinion. I'll put it to you this way. There are some shortcut formulas. I shouldn't say that. There are some formulas that are far uglier than the formulas that I'm showing you. Supposedly, if you had like a lot of numbers here, I guess they could save you some calculation time, but you would never, and there's no reason why you would, understand why you were putting the numbers in that, because it doesn't show that we're getting averages of variances. It's not going to show that we're looking at the difference between each sample mean and the overall mean. It's just a number crunching kind of thing. These are what I would call more or less explanation formulas. We started with those graphs, and these formulas are showing you exactly what happened in those graphs.
So you give us 5 things on a test, and I'm not going to get finished with the test.
Well, should you be required to work this problem out fully on the test? I assure you there will only be one of them.
So this problem's going to be the test?
Not on the test next week.
Oh, okay.
Okay, this is later. Yes, draw a line by, this is for later. Now, one thing I will tell you is that by the time you work 3 of these, you're going to think, okay, please put one of these on the test. Because now there is another part that I won't go into tonight that's maybe a little bit more of a twist of logic, not that much really. But this is almost like just follow the recipe. I'm going to give you the formula for MSTR, the formula for MSE, and the formula for X bar bar. So all you have to know, and I may even give you this formula, and I'll give you the formulas for degrees of freedom. So there's not going to be a lot of, I guess, memory kind of stuff. You just kind of have to follow through with it. And I'll admit, this is a lot to look on, especially on just one sheet, a little thing right here. But I'm telling you that the third time you work one of these, yeah, it's just not that bad. So.
I just get tired of punching in the formulas.
While I have this here, if you would take your calculator for a moment and hit Stat and Edit. And what we want to do is in lists 1, 2, and 3, we want to put the original numbers. So in list 1, you're going to have 9, followed by 3 10s, followed by an 11. Right here, I'm putting these numbers. then these, just the original data that was in there. So in list 2, I'm going to have a pair of 14s, a 15, and a pair of 16s. And in list 3, I'm going to have 5 20s. And so if you would hit now Stat and Tests and arrow up 1 to ANOVA. It'll say ANOVA and open parenthesis, and then hit Enter. It should say ANOVA parenthesis on your calculator right now. And sometimes if you had some other stuff in your calculator, it'll put it on the end of that. You just have to do what we just did again. Clear that and then come back. You need to have ANOVA parenthesis in one line. Then hit second L1 because we had some data in L1. Then have a comma, second L2, comma, second L3, and then close that parenthesis. Right here. Mm-hmm. Then L2. Mm-hmm. And then close the parenthesis. You hit Enter, and you will see the F is 250. That's what we got. The p-value there is 1.66 times 10 to the minus 10th. So you'd have 9 zeros before you got to a number. That's a small p-value. You're going to reject HO. Then for factor, that's the same thing as treatment. And if you read a lot of books on ANOVA, sometimes they're going to call it mean square treatment like I have it. They're calling it factor here, but I've really never seen it called MSF. I have seen it called MSG for mean squares for groups, and MSB for mean square between groups. So, I mean, there are different the MSE is always the notation for that. But anyway, you can see that the MS for that, the mean square for the factor, is 125. That's MSTR. If you arrow down, you'll see arrow and then error, and then when you the bottom thing there is the mean square. It's not the very bottom thing, but under error, MS is 0.5, and that's what we had. So it had the F, it had the MSTR, MS for the factor, and then the mean square for the error. Of course, we went through all of this other stuff to end up with exactly that. Certainly faster than what we did. But I think that there's an advantage to working out a small problem by hand. And believe me, this is about as small as I can get it. You know,
And we had 5 A, B, C, D, E,
and 30 in each group. Then we're back into that prison situation again here. Something to do while you're held as a political prisoner. I don't know if I would do that. I might flip the coin thing. I don't know.
Scratch it into your walls, and when the guard comes up, all your walls are filled with tally marks.
Something like that. Okay, what I'm going to do really quick now is, we're going to have the same hypotheses. Remember, HR was at least one of the following is true. HO was that they're all equal. And we're going to reject HO if F test is greater than 3.9. It's the same as it was before because we still had 3 groups of 5. And the F test was equal to MSTR over MSE. And the MSTR is going to be 125 because we had the same means, 10, 15, and 20. So now what we have to do to get the rest of this problem is compute the three variances and get the MSE. So I'm going to write down the numbers that we have now. Remember, x bar A was equal to 10. X bar B was equal to 15. And X bar C was equal to 20. So again, that's all, the same means, the same MSTR. So now I'm going to get the variances. So x of I minus x bar, and then square those. So I'm subtracting 10. That's 194. And so S squared A is equal to the sum of the squared deviations divided by n minus 1. Don't take the square root. So 194 divided by 4, I believe that's 48.5. Then I'm going to do the same thing with the other two groups. So S squared B is going to be 186 divided by 4, and I believe that's 46.5. So you get a good review of deviations and squared deviations and all of that. It's only because you're watching me do it instead of doing it yourself. In my class today, I had them do this part by themselves. They didn't have any problem with it. So again, all of that I have, you should have been able to do that before you walked in the door today. Compute means, compute variances. You might have had to think back and say, oh wait, variance just means I don't take the square root. It's S squared instead of S. So then we've got MSE is just the average of those three variances. What did you get when you did that? 65.67? 65.7? So we just put that over here. About 1.9 around. might be a little more on the decimal thing. The top one, the F, 1.90, about 1.904. At any rate, it's 1.9 is not greater than 3.9, so we fail to reject HO. Mu A equal mu B equal mu C could be true. We don't have strong enough evidence to say that there are any inequalities there. They could all be the same. And if this were like 3 methods of doing something and we were measuring productivity, we should be indifferent as to which one we used because we can't show that there's a difference between them. In the other example, clearly, even if you looked at the graphs, if bigger was better, you would want to be in the first problem, you'd want to be use method C or method 3, the one on the far right. One of the things that just in terms of thinking for next week is there really is a connection here. On the top, whether it's an F test or a T test or a Z test, what's the size or the difference between means or proportions that we're looking at? On the bottom, how spread out are the data? That's what standard error is getting. It's measuring it in a lot of different ways. It's what mean square error gets as well. How spread out are the data? So we look at the ratio of effects or differences between means and proportions divided by how much error. And the bigger that ratio is, the more likely we can say it's not just error. There really is a difference between means or proportions or whatever. And I think that's one thing about the F test is, you start thinking, and we have been having it that way, but it's clearer, I think, that we're looking at a ratio just because you got the MSTR over MSE thing. There actually is another part to this problem, but there's no way we're going to talk about it until after you take the test.